The future belongs to those who understand data, and every click, every number, every decision, and powered by intelligence.
With Python, you don't just analyze data, you control it. You visualize it, and you turn it into opportunity. At EDXcellence, we train you with real-world projects and practical skills. Master data science with Python. Build your future with EDXcellence.
Data analytics functions as a retrospective practice, looking backward at historical records to report on events that have already occurred. In a retail environment, this involves reviewing previous grocery store receipts to identify which specific locations lost money on certain products during the last quarter. While this reports the exact location of the loss, it lacks a mechanism to algorithmically determine the specific inventory adjustments or pricing strategies required to recover those margins. Data science marks the transition into forward-looking prescriptive modeling. This timeline illustrates the shift. On the left, analytics plots discrete data points from the past. On the right, data science generates a probability cone to calculate future outcomes. Moving from observation to prediction requires the construction of a multi-tiered cyclical pipeline. This architecture relies on 4 sequential components: relational storage, programmatic cleaning, statistical probability, and machine learning. Building this technological stack begins with the foundation layers and moves upward through the logic engine. This architectural stack transforms a library of historical records into a predictive engine that updates its own logic as market conditions change. The architecture begins at the data lake, a massive, unstructured pool of heterogeneous raw information stored exactly as it was captured. Before this information is usable, we execute data mining to extract relevant subsets from the chaotic lake. These subsets are moved to a data warehouse, where the information is organized into structured grids. In a hospital database, these grids function as distinct tables. A doctor table connects to a patient table, which links to a record of medical operations. Data scientists use SQL, or structured query language, to map and query the exact relational architecture between these tables. When datasets exceed the limits of a standard relational database, engineers implement big data technologies like Hadoop to manage storage at scale. Without this relational storage layer, the predictive algorithms that follow would have no structured logic to process. Real-world data is inherently noisy, arriving with missing values, inconsistent date formats, and entry errors that disrupt analysis. Data cleaning is the process of filtering out these anomalies and transforming the information into standardized numerical arrays. This transformation is managed within Python, typically using the Jupyter Notebook environment to write and test the cleaning logic. Python acts as the logic engine, utilizing libraries like pandas and NumPy to execute the complex numerical transformations required to make the data machine readable. This allows for an exploration phase, where the data scientist analyzes the clean arrays to identify statistical correlations before building a predictive model. The predictive accuracy of the final model is restricted by the rigor of this cleaning layer. Erroneous inputs result in unreliable outputs. Transitioning to the core of the pipeline involves moving from explicit, hard-coded rules to the application of statistical probability. Machine learning recognizes patterns by processing massive volumes of labeled training data. A convolutional neural network, or CNN, deconstructs images into mathematical vectors, isolating features like ear shapes, leg structures, and torso outlines to determine identity. The model weights these isolated features against the patterns it learned during its training phase. The final output is a calculated probability, in this case a 95% certainty that the input matches the classification for a dog. This predictive foresight allows systems to autonomously solve recognition and forecasting problems that are too complex for manual human analysis. A high-probability algorithmic output holds no value if it cannot be interpreted by business leaders who lack technical training. Data visualization tools like Power BI serve as the final translation layer, converting the underlying architecture into a color-coded dashboard. These dashboards render probabilistic findings into actionable insights. This creates a feedback loop. feeding new results back into the foundation layer, refining the model. Maintaining this pipeline requires constant management of data privacy and the scaling of infrastructure to handle increasing volumes of information. As market conditions shift, the system requires continuous architectural iteration to maintain the accuracy of its predictions. Data science functions as a living architecture, refined by its own predictions to construct a reliable model